For the last few lectures, we've been focusing on gravity, orbits, tides, and black holes. Now it's time to shift our gaze to a different fundamental force, electromagnetism, specifically electromagnetic radiation. As astrophysicists, our self-appointed task is to solve the mysteries of the cosmos. And the only clues we get, with few exceptions, are from the trickle of radiation that arrives at the Earth from distant sources. So we need to become best friends with electromagnetic radiation. In classical physics, that is not quantum physics, electromagnetic radiation takes the form of waves. So first let's talk about waves. You get waves whenever there's some physical quantity that varies smoothly throughout space and time, like the height of the surface of a pond, or the pressure in the air of a room, that when it's disturbed, produces an oscillating pattern. Drop a stone in the pond, and ripples propagate outward. Clap your hands in the air, and the pressure rises and falls in a pattern that moves outward and is perceived by your ears as sound. No matter what kind of wave it is, you can define the wavelength, lambda, as the distance between the maximum values of whatever is waving, say between the crests of a water wave. And you can define the frequency, nu, as the rate at which the pattern oscillates, how many times per second the height of the water bobs up and down, completing a cycle. When you multiply wavelength and frequency, you get the wave's phase velocity, the speed with which the pattern moves, which for electromagnetic radiation is the speed of light, c. So lambda times nu equals c. Now with light, it's a lot less obvious what is waving. It's not like the air or anything material, it's the more abstract oscillations of electric and magnetic fields. The electric field is a vector whose magnitude wobbles back and forth, while the magnetic field does the same thing but tilted by 90 degrees, and the whole pattern moves in the direction perpendicular to both vectors. The wavelengths of visible light range from 0.4 to 0.7 microns. The corresponding frequency, nu, is just under 10 to the 15th cycles per second, or hertz. But that's just a tiny slice of the whole spectrum. Toward longer wavelengths, there's infrared radiation. And when the wavelength exceeds a millimeter or so, we start calling them microwaves and then radio waves. Likewise, on the short wavelength end, we have ultraviolet radiation, and shorter than about 10 nanometers, we call them X-rays and then gamma rays. All these names and boundaries, they're arbitrary. They're based on the different technologies that humans use to study electromagnetic radiation. Nature herself makes no sharp distinctions. Now, I said earlier that waves are produced by a disturbance, dropping a stone in the water, clapping your hands. So what kind of disturbance produces electromagnetic waves? The answer is the acceleration of an electrically charged particle. When a charge accelerates, it radiates. And it goes backwards too. Charges can absorb electromagnetic energy, causing them to accelerate. These facts come from solving Maxwell's equations of electromagnetism, and I can show you what happens graphically. Consider a positively charged particle at rest. Coulomb's law says that it produces an electric field pointing away from the charge and varying in strength as 1 over r squared. We can represent that field with lines that emanate from the charge and diverge into the surrounding space. The electric field is everywhere parallel to these field lines. If we now shake the charge, the field lines quiver. A disturbance propagates outward in the form of sharp bends in the field lines. That's a transverse pattern of electric fields, which is accompanied by magnetic fields. The pattern and the energy of those waves depend on the details of the acceleration. An electron slowing down in a block of lead produces a certain pattern. An electron whirling around a magnetic field produces a different pattern, and an electron falling from one orbit to another inside an atom produces yet another kind of radiation. But if the charges are moving randomly, if there's zillions of charges rattling around, colliding with each other, and they've been at it a long time, enough to reach a steady state, then there's an enormous simplification. The radiation takes on a universal character, depending only on the temperature. We'll see later what that looks like in this lecture. For now, though, let's take leave of waves and talk about particles. In quantum theory, we learn that if you look closely enough at electromagnetic energy, you'll see it comes in tiny lumps called photons. In principle, you could count the photons arriving from the sun, like counting raindrops falling from the sky or grains of sand in an hourglass. But photons have some weird properties that normal particles do not have. So let's first talk about normal particles. Think of a box full of tiny particles, like little billiard balls whizzing around and knocking into each other. This is an idealized model of a gas. Each particle has a mass, m, and a speed, v, from which we can compute the particle's kinetic energy, 1/2 mv squared, and its momentum, mv. We'll use the symbol epsilon for the energy of a single particle to distinguish it from the total energy, E, of the entire gas. Now, what about photons? The first thing to know about photons is they have zero mass. Second thing is they always travel at the same speed, c, 3 × 10⁸ meters per second. You can slow them down by putting obstacles in the way, like a piece of glass, but in empty space, photons always travel at speed c. Now here come some even weirder facts. Even though they have zero mass, photons do have energy and momentum, but the equations are different. The energy of an individual photon is h times nu, or equivalently hc over lambda. That's right. Even though it's a single particle, a photon has an associated frequency, nu, and a wavelength, lambda. That constant of proportionality, little h, that's Planck's constant again. Whenever you see little h in an equation, you know you're dealing with quantum theory. Now, I realize it's hard to imagine something that's both a particle and a wave. I try to imagine photons as wave packets, glowing little bundles of energy with dark and light fringes. But that's just a mental image, and in quantum theory, none of our mental images are quite right. As for the momentum, that turns out to be equal to the energy divided by c. So the momentum of a single photon is h nu over c. That's it for the individual properties of particles and photons. Next, let's talk about their collective properties, the entire gas of particles, and the photons that they produce and absorb. That means we need to do some thermodynamics. Let's say our box has a volume V, and we fill it with a certain number of particles, capital N. We define the number density, little n, as the number per unit volume. And into the box, we inject a total energy of E. That'll be the sum of all the kinetic energies of all the particles, which is constant in time because the box is sealed up tight. If we now let the particles knock around for a long time, their positions and velocities become randomized. Particle could turn up anywhere in the box with equal probability. And the particles will come to share the total energy, more or less equally. That's the conceptual basis of temperature. The temperature, T, is defined to be proportional to the average energy per particle. For an ideal gas, that proportionality constant turns out to be 3/2 K, where K is Boltzmann's constant. Whenever you see little k in an equation, you know you're doing thermodynamics. The numerical value is 1.4 times 10 to the minus 23 joules per Kelvin. The general rule is that the average energy is 1/2 kT times the number of independent ways that a particle can store or exhibit energy. The technical term is the number of degrees of freedom. Our billiard balls can move in 3 dimensions, so the kinetic energy has 3 terms. 1/2 m times Vx squared plus Vy squared plus Vz squared. And each one counts as a degree of freedom, so the average energy per particle is 3/2 kT, which means the energy density, U, the total energy per unit volume, is equal to 3/2 times the number density times kT. So the temperature of a gas is a scale for the energy associated with the random motions of the particles. In addition to energy, the particles have momentum, and the scale for that is pressure. The particles are constantly knocking into the walls of the box or any surface that we might insert in the gas, and those collisions exert a force on the surface. That's pressure. To simplify the math, we'll imagine a universe in which the particles can only move in one direction. They can move back and forth in, say, the x direction, but not any other. When a particle with speed v hits the wall, it reflects back with a speed v in the opposite direction. Its momentum changes from plus mv to minus mv, a change of minus 2 mv. And since momentum is conserved, the wall must have absorbed a momentum of plus 2 mv. It feels a push. And that keeps happening as more and more particles hit the wall. So, in a time delta t, how much momentum does the wall absorb? Well, let's say all the particles have the same speed, v, and half are moving to the right and half are moving to the left. The particles that hit the wall are the ones that are moving to the right and that start out within a distance of v delta t from the wall. If we now focus on an area delta A of the wall, that singles out a box with a volume of v delta t times delta A. So the total momentum absorbed by the wall will be the momentum from each collision, 2mv, times the number of collisions, which is equal to n-halves, the number density of particles moving to the right, times v delta t delta A, the volume of the box. Force is momentum per unit time, and pressure is force per unit area. So to get the pressure, we divide our equation by delta t and delta A. That gives nmv squared. And since mv squared is twice the kinetic energy per particle, epsilon, we can also write that as 2n epsilon. Now, we've been assuming all the particles have the same speed v, but that's not true. There's a whole range of speeds. So we should replace epsilon by its average value, which, as we discussed a moment ago, would be 1/2 kT in a one-dimensional universe. So in the end, the pressure is 2n times 1/2 kT, or simply nkt. We just derived the ideal gas law. Pressure is proportional to number density and temperature. We did it for a one-dimensional gas, but in 3D you end up getting the same equation. Now, those of you coming from a background in chemistry might be used to seeing this equation as P equals nRT. It's the same thing. The R is just K, but in chemists' units. They like to count particles in units of moles, but physicists just tend to count the particles individually. One more thing about the ideal gas. Suppose we pop a tiny hole in the wall with an area A. Gas particles will start leaking out, and the gas will lose energy. So what's the rate of energy loss? In our 1D universe, the number of particles that leak out in time delta t is equal to the number density of right-moving particles, that's n/2, times the volume of that same box, V delta T delta A. And each one has an energy of epsilon. That gives delta E equals epsilon times n over 2 times V delta T delta A. Let's divide by delta A and delta T to give the power per unit area. That's the flux of escaping energy. And again, since there's a range of speeds and energies, we should take the average. The important thing is that it's proportional to nV epsilon, which also turns out to be proportional to the temperature to the 3/2 power, though I won't take the time to work that out. I've gone into enough detail now about the ideal gas for our purposes. The ideal gas will be a useful idealization throughout this course, when we talk about the atmospheres of planets and the interiors of stars. The ideal gas law, P equals nKT, will be another loyal companion, along with Kepler's third law. I also wanted to spell out the properties of the ideal gas to allow you to compare them to the properties of a gas of photons, which are not intuitive. The derivation of the corresponding equations for photons is beyond the scope of this course, but at least you'll now be able to appreciate them better by making these comparisons. The first thing to know is that photons, unlike particles, don't collide with each other. They sail right through each other. The only things photons interact with are charged particles. So in order to randomize the positions and energies of photons, you need to have charged particles around, which are themselves in thermodynamic equilibrium. So we'll fill our box with charged particles that are colliding all the time, producing momentary accelerations, and thereby producing and absorbing photons. Let's start our comparison with the average energy per particle. For an ideal gas, that was 3/2 kT. For the photons, turns out to be 2.7 kT. That's not so weird. They're both proportional to temperature. There's just a different numerical constant in front. Things get weird, though, with the number density. It goes without saying that for an ideal gas in a closed box, n is constant. The particles don't just spontaneously pop out of nowhere or vanish. Even if we add energy, speeding up the particles, their number stays the same. But photons do just pop out of nowhere whenever a charged particle accelerates. The particle flings away some of its own energy in the form of photons. Likewise, a photon vanishes when its energy is absorbed by a charged particle. So for photons, we shouldn't expect n to be a constant. If we inject more energy into the gas, speeding up the particles, the magnitude of their accelerations will rise, and they'll produce more photons. It turns out the number density of photons rises as the temperature to the 3rd power. The number density, n, is the cube of 3.9 kT over hc. By the way, both the 3.9 in this equation and the 2.7 in the other one, they're not exact. They're the first 2 digits of transcendental numbers, numbers like pi with an infinite number of digits. Next, let's compare the energy density. For the ideal gas, the energy density, U, equals 3/2 nKT. So it's proportional to nt. For photons, we just saw that n varies as t cubed. So if energy density varies as nt, we might expect the energy density of photons to vary as t to the 4th power. And it does. The constant of proportionality is traditionally written 4 sigma over c, where sigma is the Stefan-Boltzmann constant, which I'll describe in a moment. Then comes pressure. For the gas, pressure equals nKT, the ideal gas law. For photons, again, n itself goes like t cubed, so we might expect pressure to go like t to the 4th power, and it does. In this case, the proportionality constant is 4 sigma over 3c. we never notice radiation pressure because at ordinary temperatures, it's negligible. But in principle, when you're at the beach, the sunlight hitting your body is pushing you down into the sand, just a little. But inside really massive stars, the radiation pressure can be so large that it blows the star apart. Finally, let's consider the flux, the power per unit area that would emerge from a tiny hole in the box. For the gas, we said it's N times the average of V epsilon, which was proportional to T to the 3/2 power. For photons, the number density N scales with T cubed, V is always C, and epsilon is proportional to KT, so we might guess that flux is proportional to T to the 4th power, and it is. That's a very important result. The flux of electromagnetic radiation from a body at temperature T is proportional to T to the 4th power. That's important enough to deserve its own name. It's the Stefan-Boltzmann law. The constant of proportionality is sigma. That's the one that also appeared in the equations for energy density and pressure. Sigma isn't a new fundamental constant. It's a certain combination of h, c, and k, but it occurs so frequently that the abbreviation is helpful. And numerically, sigma is 5.7 times 10 to the minus 8 watts per square meter per degree Kelvin to the 4th power. The last comparison I want to make between particles and photons is in their distribution of energies. For the case of the gas, the average energy is 3/2 kT. If we pick a particle at random, we expect its energy will be about 3/2 kT, but not exactly. Sometimes it'll be a little higher, sometimes lower. It depends on its history of collisions. Likewise, the speed of a given particle is always fluctuating. A fundamental rule that emerges from classical statistical physics is that the probability to find a particle in a state with an energy of epsilon is proportional to e to the minus epsilon over kT. It's an exponential function, and it's called the Boltzmann factor. What does it mean? It means that the energy will almost always be on the order of kT. Much larger energies are vanishingly rare because of that exponential fall-off. The particles tend to share the energy equally. There's very little chance that one particle is going to end up with a disproportionate share of the total energy. From that basic rule, it's possible, although admittedly not easy, to derive the probability distribution for the energy or the speed of a particle in a gas. What makes it difficult is that there are a lot of different states with the same energy. If we change the direction of a particle's velocity, but not its speed, the particle is in a different state, but it has the same energy. That means to calculate the probability of having a certain speed, we need to multiply the Boltzmann factor by the number of possible states with that speed. And so there's a lot of bookkeeping associated with counting all of those states. But if you do go through all of that, you can derive the Maxwell-Boltzmann distribution. That's the probability distribution for particle speed in an ideal gas. It's the product of the Boltzmann factor and a factor of v squared, which comes from all of that state counting. The horizontal axis is speed in meters per second, and the vertical axis is the relative probability that you'll find a particle to have that speed. Or another way to think of it, it's the fraction of particles that have that speed at any given time. The function depends on the particle mass and on the temperature. For this chart, I chose the case of nitrogen molecules at 300 Kelvin, basically air at room temperature. The function rises from 0 to a peak at around 400 meters per second, then it falls off again. That's kind of amazing when you think about it. The molecules in the air around us are moving at speeds of hundreds of meters per second. Of course, they don't get very far before they knock into another molecule, but still, that is an impressive speed. If I turn up the temperature, the peak now spreads out and moves to higher velocities. And if we turn it down, the peak moves to the left to lower velocities. In general, the most probable speed is the square root of 2kT over m. Now let's switch to photons. Let's imagine trapping some photons from the sun in a reflecting box and measuring the wavelength of each and every one. We'll draw a wavelength scale and divide it up into bins, like ticks on a ruler, and then keep a tally of how many photons have a wavelength within each bin. Once we collect enough photons, we see there's a peak at about 0.6 microns. That is the most popular wavelength to have in sunlight. The shape of the function looks like the Maxwell-Boltzmann distribution, but it is different in detail because photons are not just everyday particles. This is called a Planck spectrum, and this curve is for 5,800 degrees Kelvin, approximately the temperature of the sun's outer layers. The bright star Vega is hotter than the sun. It's closer to 9,500 Kelvin, so its spectrum is shifted toward higher energies, which means shorter wavelengths. And the faint nearby star, Proxima Centauri, is only about 3,000 Kelvin, so its photons generally have lower energies and longer wavelengths. I drew these probability curves to allow a direct comparison with the Maxwell-Boltzmann distribution. But the Planck spectrum is usually expressed differently, not as the number of photons per unit wavelength, but rather as the flux per unit wavelength, the so-called flux density. If we pop a tiny hole in the box, the total flux that leaks out is sigma t to the fourth, as we said earlier. But what are the contributions to that flux from photons of different wavelengths? That's the flux density, power per unit area per unit wavelength. When we measure the flux density of the sun as a function of wavelength, we find it's a pretty good fit to a theoretical Planck spectrum. It peaks at around 2 kilowatts per square meter per micron at a wavelength of half a micron. Why doesn't it fit exactly? The Planck spectrum describes the radiation you get from particles that have been knocking around long enough to reach a constant temperature. They're in thermodynamic equilibrium. It's often called a blackbody spectrum because technically the derivation relies on the material being a perfect absorber of photons and therefore black. Now, the sun, or any other real object, doesn't meet those criteria exactly. The sun is not all at one temperature. It gets hotter as you go deeper. And the sun's material is not perfectly absorbing, but the spectrum of the sun and other stars are nevertheless reasonably well described by the Planck function. That's what allows us to say, with a straight face, that the glowing white sun is approximately a black body. Let's look at the Planck spectrum on logarithmic axes. That way, we can let the wavelength scale range over a factor of 1,000, from ultraviolet to infrared, and we can let the flux density scale over a factor of 1 trillion. We won't have much occasion to use the formula for the Planck spectrum in all of its glory, but we will make frequent use of two properties of the Planck function that you can see on this chart. First, as we increase the temperature, the curve lifts up vertically. Hotter sources produce more radiation at all wavelengths. The area under each curve, the integral of flux density over wavelength, is the total flux, which is equal to sigma times t to the fourth. That's the Stefan-Boltzmann law. You double the temperature, and the flux rises a factor of 16. Second, as we increase the temperature, the peak of the spectrum shifts to shorter wavelengths. At room temperature, 300 Kelvin, almost all the energy comes out in the infrared. It peaks at around 10 microns. As we dial up the heat, the peak shifts to shorter wavelengths. That makes sense because we expect the typical photon energy, hc over lambda, to be on the order of kT. That implies lambda should be of order hc over kT. It should be inversely proportional to temperature. When you do the math exactly, you find that the peak of the spectrum occurs when lambda is about 1/5 of hc over kT. That's called Wien's law. We can also write it as a scaling relation. Lambda peak equals 10 microns times T divided by 300 Kelvin to the -1 power. Those two laws, Wien's law and the Stefan-Boltzmann law, will also be loyal companions, along with Kepler's third law and the ideal gas law, helping us make sense of the cosmos. I should point out, though, that although the stars, the planets, and many other astrophysical sources have Planck-like spectra, not all light sources do. A laser, for example. In a laser, circumstances are contrived so that all the photons have the same wavelength. Likewise, radio waves from your cell phone don't follow a blackbody spectrum. They're produced by forcibly shaking electrons in an antenna at a single frequency. And X-rays in a hospital scanner don't follow a blackbody spectrum either. They're made by crashing high-energy electrons into a dense metal. They're not from random thermal motions. Some other everyday light sources, though, are at least roughly blackbodies. A candle flame, a campfire, an incandescent light bulb. To make a really accurate blackbody for a laboratory turns out to be difficult, though. It requires careful engineering. You can buy one from the National Institute of Standards and Technology, but they're pricey, and no single device can cover the whole spectrum. Which makes it all the more remarkable that the universe provides, for free, a natural blackbody more perfect than any laboratory device. We are constantly bathed by photons whose spectrum follows the Planck function with an accuracy better than 1 part in 10,000 and a temperature of 2.7 degrees Kelvin. According to Wien's law, that corresponds to a wavelength of 1 millimeter in the microwave band of the spectrum. Why is the universe permeated with this microwave blackbody radiation? It's a clue that at some point in the past, the universe was itself a gas of particles at a single temperature in thermodynamic equilibrium, long before it became the place we know today, with tiny pockets of extreme heat and vast expanses of frigid cold. This so-called cosmic microwave background radiation is some of the best evidence we have for the Big Bang. More on that topic, much more, toward the end of this course.